Okay, in this video, we're going to be looking at multi-stage experiments with tree diagrams and geometric probabilities. And in this particular video, we're going to talk about multi-stage experiments, independent events, modeling games. And also, we're probably going to look at geometric probability or area models. Let's start off with tree diagrams. Suppose the spinner is spun twice. The tree diagram shows all the possible outcomes. Okay. Now, in this one, this looks black and white, but we do have a red, a yellow, and a blue. Okay, so the first spin is going to be either blue, it's either going to be red or yellow. And that probability is, for each one of those, 1/3. Okay, and then on the second spin, if the first spin was blue, then the second spin could be either blue, red, or yellow. And again, that probability is going to be 1/3 for each one of those, because there are 3 colors on that wheel. Now, if the first spin was a red, then again, blue, red, or yellow could be on the second spin. And again, that probability is still going to be 1/3. And the same thing for the yellow. If the yellow was on the first spin, then either blue, red, or yellow could be on the second spin. Each one of those probabilities, again, would be 1/3. And on this far right-hand side, you'll see all the possible outcomes here. A blue, blue and red, blue, yellow. Then red, blue, red, 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 yellow. Then yellow, blue, yellow, red, yellow, yellow. So here you see 9 possible outcomes for this particular situation if the spinner was spun twice. And as you can see here, that's the sample space right here that I just mentioned. That's your sample space. And here the probability of each outcome would be 1/9. Okay, so here, because there are 9 possible outcomes, and of course, only one of these can happen, so it'll be 1/9 for each one of those probabilities. Alternatively, we can generate the sample space using a table. Like on the first draw would be a blue, yellow, red. The second draw would be blue, yellow, red. So here, blue and the blue would be here, blue and yellow would be here, blue and red would be here. And we can continue this pattern with the rest for the yellow and for the red. So you can see here that there are 9 possible outcomes. So if I want to find the probability of getting a yellow and a blue first, well, the yellow first and then blue second, that would be this outcome, 1/9. All right, an example of this. Suppose we toss a fair coin 3 times and record the results. Find each of the following. That is the sample space for this experiment. Okay? Now, if we toss a fair coin 3 times, then that means this will be the sample space for that whole thing. Heads, 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 tails, heads, tail, heads, tails, heads and heads, tails, 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 heads, tails, heads, tails, and heads, tails, tails. Now, you can, if you want to, draw a tree diagram. I'll show you how that's done. Because on the first coin, you're either going to have heads or tails on the first flip. Let's just say first flip. Then on the second flip, if the first flip is heads, then the second flip could be either heads or tails. Or if the first flip was tails, then that means the same thing, heads and tails. And then you got the third flip of the coin. If the first one's heads and the second one is heads, then the third one could be either heads or tails. Well, if the first one is heads and the second one is tails, then you can either have heads or tails on the third flip. And then for this one, same thing, heads or tails. And then the next one, heads or tails. And then all the possible outcomes from that sample space, you have heads, heads, heads. That's one outcome. Then heads, heads, and tails. That's the second outcome. Then heads, tails, heads. That's the third outcome. Then heads, tails, tails. That's the fourth. And then for tails, you got tails, heads, and heads. Then tails, heads, and tails. Then tails, tails, heads. Then finally tails, tails, and tails. Okay. You can generate that by using a tree diagram. That's pretty much the easiest for me to use. So that tree diagram does give you that entire sample space, which is this. And then let's look at part B, the event A of tossing two heads and one tail. Okay, now let's look at the events that has two heads and one tail. Here's one, two heads and one tail. That's heads, heads, tails. Here's another one, heads, tails, heads. And here's the third one, tails, heads, heads. That's two heads, one tail. So that's your event A, which is your subset of your sample space. And part C, the event B of tossing no tails. Well, they all have to be heads, so that's only one event that can happen. Heads, heads, and heads. H, H, H. And then event C of tossing a head on the last toss. Okay? Has to be heads on the last toss, so heads, heads, and heads would work. Heads, tails, and heads. Then tails, heads, heads. And then tails, tails, heads is another. So those are the four possible outcomes of tossing a head on the last toss. Another example would be rolling a fair die and finding the probability of event A, rolling double sixes. And in this case here, a pair of fair dice. Now here, on the left side, you see the number on the first die, which is 1 through 6, and the number on the second die, also 1 through 6. And you see all 6 possible outcomes from this. All 36 possible outcomes. Okay? And there's only one way to roll double sixes, which is, of course, 6 and 6. There's only one way to do that. So that probability of rolling double sixes will be 1 out of 36. Also find the probability of rolling a sum of 7 or 11 when rolling a pair of fair dice. Okay, again, there are 36 possible rolls. And as you see on this next page, you'll see that there are 1, 2, 3, 4, 5, 6 ways of rolling a 7. So the probability of rolling a sum of 7 will be 6 out of 36. Also, you'll see that only 2 ways to form a sum of 11. Okay, there should be 2 ways for a sum of 11. Because the sum of 11 would be 5 and 6, and then 6 and 5. So 2 out of 36 would be the probability of rolling a sum of 11. Okay, now to answer the question of the probability of rolling a 7 or 11, as you can see here, so the sample space for that experiment will be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. But the sample space is not uniform. That means that the probability of the given units are not equal. So that means that the probability of rolling 7 or 11, that's 6 out of 36, plus 2 out of 36, which will be 8 out of 36. Now, In the event they ask you to reduce this in simplest form, 8 out of 36 can be reduced by dividing the numerator and the denominator by 4, which will be 2 ninths. Okay. And what do we mean by not uniform? That means that these individual probabilities are not going to be not equal to each other. Okay. Okay, another example would be this: a pair of dice is rolled. Let E be the event of rolling a sum that is an even number, and F the event of rolling a sum that is a prime number. Find the probability of rolling a sum that is even or prime. Okay. In other words, in symbolic notation, the probability of the union of E and F. Well, if we take the union of E and F, it would be those numbers there: 2, 4, 6, 8, 10, 12, 3, 5, 7, 11. That's 2, 4, 6, 8, 10, 12. That's the set of prime numbers. The set of even numbers. And then you got 2, 3, 5, 7, 11. Those are your prime numbers. The union of those two will be this entire set. Okay. And then you can use this table to add up those individual probabilities. The probability of event 2 for 2 would be 1 out of 36. For 4, it'll be 3 out of 36. For 5, it'll be 4 out of 36. For 6, it'll be 5 out of 36. For 8, 5 out of 36. For 10 is 3 out of 36. And then for 12, it'll be 1 out of 36. And then the probabilities for your prime numbers: for 3, that's 2 out of 36. For 5, that's 4 out of 36. For 7, 6 out of 36. And for 11, 2 out of 36. Add all those numbers together. The common denominator is 36. Just add the numerators and keep the same denominator. It'll be 32 over 36. And if you were to ask to reduce this, this will be 8 ninths. Just divide the numerator and the denominator by 4. Okay, another example. Well, the alternate solution to that example would be this. We can use the one of the theorems or one of the properties for probabilities here. Here we can add the two probabilities and then subtract off the element or the event that's common in both E and F. E is the set of even numbers for a pair of fair die. That's 2, 4, 6, 8, 10, and 12. F is the prime numbers for a pair of fair die. 2, 3, 5, 7, 11. Okay, here you can see they're not mutually exclusive because 2 is common in both E and F, so that's why they're not mutually exclusive. Okay, so the probability of event E happening would be 18 out of 36. The probability of event F happening would be 15 out of 36. Okay, then you have to subtract off what's common in both, the 2, which is 1 out of 36, to avoid double counting. So 18 plus 15 minus 1 would be 32, and then over 36, or 8 ninths. So that's the probability of rolling either a 7 or 11. Okay, and here's another way that you could do this. Now here they use the complement of the union of E and F. Okay, so if E union F is this: 2, 3, 4, 5, 6, 7, 8, 10, 11, and the union of those two will have to be 9. Okay, and there are 4 ways of getting a 9, so the probability of the complement of E union F will be 4 over 36, which means that the probability of the union of E and F will be 1 minus 4 over 36, which will be 32 over 36, or 8/9. So as you can see, there are several ways that you can attack that particular problem or find out what the probability of rolling a 7 or 11. You just have to pick out which one is easier for you to work with. All right, let's look at more multi-stage experiments. The box in the figure A contains one colored ball and two white balls. If a ball is drawn at random and the color is recorded, a tree diagram for the experiment might look like the one in figure B. Because each ball has the same chance of being drawn, we might combine the branches and obtain a tree diagram as shown in figure C. So here, figure A, you have one colored ball and two white balls. If you were to do a regular tree diagram, then you have a white, and a colored ball. Each probability is 1/3. But notice that you have two white balls. If we combine those, we can say 1/3 and 1/3, that would give us 2/3, which is the probability of drawing a white ball. That's 2/3, and then the probability of drawing a colored ball will be 1/3. So here, this one would be much simpler to do it this way. Because you have a white ball, and there are two of them, so that's 2 out of 3, and only one colored ball, that's 1 out of 3. Suppose the ball is drawn at random from the box in the figure and its color is recorded. The ball is then replaced and the second ball is drawn and its color is recorded. The sample space for this two-stage experiment may be recorded using ordered pairs as this. 2 colored balls, and then a colored and a white, then a white and a colored, and then 2 whites. That will represent your sample space. The tree diagram for this experiment is shown below. So in the first draw, you're going to draw either a colored ball or a white ball. There's only one colored ball, so that's 1/3. There are 2 white balls, so that's 2/3. On the second draw, now here on the second draw, you're still going to have 3 balls in the box, because that on the first draw, you're going to put the ball back in the box, so you'll still have 3 balls in the box to draw from. So in the second draw, it's still going to be 1/3 for the colored and 2/3 for the white ball, and the same for this branch here. So here's what your outcome looks like. You can have a colored and a colored ball, which is this outcome, a colored ball first and then a white ball second, that's this outcome, then a white ball first and then a colored ball second, that's this outcome, then colored ball, the white ball and the white ball, that's this outcome here. And that probability is this. You're going to multiply each of the probabilities that are along the branch. For 2 colored balls, you're going to have 1/3 times 1/3, which is 1/9. And then for a colored ball and a white ball, that's 1/3 times 2/3, which is 2/9. And then for a white ball and a colored ball, 2/3 times 1/3, which is 2/9. And then for a white ball and a white ball, that's 2/3 times another 2/3, which is 4/9. Okay. Now that represents a tree diagram with replacement, because the ball is going to be drawn the first time, and then you're going to put it back in the box and then draw a second time. For all multi-stage experiments, the probability of the outcome along any path of a tree diagram is equal to the product of all the probabilities along the path. Suppose 2 balls are drawn one by one without replacement. So that means you're going to draw a ball, one of 3 balls, out of the box, and then you're not going to put it back in. So that means you're going to have 2 balls left to draw out of the box. Okay? Now let's look at this situation here. On the first draw, you're going to draw a colored ball or a white ball. For a colored ball, this probability is 1/3. For a white ball, it'll be 2/3. But on the second draw, there's only one. You're not going to put the. Let's say you draw a colored ball, and that colored ball is not going to be put back in the box. So that means that there are no colored balls in that box. Keep in mind that you only have in the box a colored ball and a white ball, and 2 white balls. Okay? So if a colored ball is taken out of the box, on the second draw, you're only going to have 2 white balls in there. So the probability of drawing another colored ball would be 0/2. Or 0. That's an impossible event. Because the colored ball is taken out. So you're not going to be able to draw another colored ball again. Okay? And then, or, if the first draw is a colored ball, then drawing a white ball will be 2/2. Because all you have are 2 white balls in the box. Okay? Now, if the first draw was a white ball, then you're going to have a colored ball and a white ball. So that probability is now 1/2, not 1/3, because this is without replacement. Okay? And then, if the first draw was a white ball, then the probability of drawing a white ball again, now you have 2 balls, a white and a colored ball, that probability is now 1/2. Okay? So on the second draw, usually the denominator is going to decrease. Okay? Because you're not putting that particular item back in. That means without replacement. Okay? And this is what the outcomes look like. 2 colored balls, which means that the probability for that is going to be 0. That's 1/3 times 0/2, which is 0. Then you have a colored ball, then a white ball, so now you have 1/3 times 2/2. 1/3 times 2/2, well, 2/2 is going to be 1 whole, so 1 times 1/3 will be 1/3. And then for a white ball and a colored ball, that's 2/3 times 1/2, which will be reduced to 1/3. And then 2 white balls will be 2/3 times 1/2, which is 1/3. Okay. So this is an illustration of drawing 2 balls, 1 by 1, without replacement. Okay. Let's define independent events. Independent events are when the outcome of one event has no influence on the outcome of the second event. Independent events are when the outcome of one event has no influence on the outcome of the second event. If 2 coins are flipped and event E is obtaining a head on the first coin and event 2 is obtaining a tail on the second coin, then E1 and E2 are independent events because one event has no influence on possible outcomes. Okay? The outcome of me getting a tail will have nothing to do or will not have any influence of me getting a tail on the second. So that's why they're called independent events. And this is what a tree diagram of what independent events look like. On the first flip, you have heads or tails. Each of those probabilities is 1/2. And then on the second flip, heads or tails, if the first flip was heads. And then for tails, if the first flip was tails, then it'll be either heads or tails. Notice those probabilities on that branch is 1/2. So the probability of me getting 2 heads on this outcome will be 1/2 times 1/2 will be 1/4. And this continues with heads and tails. That's also 1/4, and then tails and heads will be 1/4, and then tails will be also 1/4. So this is an example of independent events. So for any independent events E1 and E2, the probability of the intersection of E1 and E2 would be just the product of those two probabilities, the probability of E1 times the probability of E2. All right, let's look at this example here. The figure shows a box with 11 letters. Some of the letters are repeated. Suppose 4 letters are drawn at random from the box, one by one, without replacement. What is the probability of the outcome BA, BY with the letters chosen in exactly the order given? So here we have a box with 11 letters, and it spells the word probability. So we want to find the probability of getting the outcome BA, BY when those letters are chosen in the exact order. So we're only interested in only the tree branch leading to the outcomes BA, BY. So here, the first letter we want to draw is a B, so the probability of drawing a B would be 2 over 11, because in the word probability there are 2 B's. Then the next letter would be A. Now, we're not replacing it, so that means that the B is drawn, that means that there are going to be 10 letters left. So that's why the denominator is 10. But there's only one letter in one A in the word probability, so it would be 1 out of 10. Then the B and the A are not replaced, so that means that there are going to be 9 letters remaining. And there's only one B left. Why is that? Because the first B is already drawn, so that means that there's only going to be one B left. So the probability of drawing that second B out would be 1 out of 9. And then this time, if the B, the A, and the B are drawn, that means that there are 8 letters remaining. So there's only one Y left in that box. So that probability would be 1/9. Okay. And it explains that the probability of the first B is going to be 2 out of 11, because there are 2 B's out of 11 letters. And then the probability of the second B will be 1/9, because there are 9 letters left after one B and one A have been chosen. So the probability of selecting the letters B, A, B, Y in that order would be 2/11 times 1/10 times 1/9 times 1/8. Multiply that out, you get 2 over 7,920. And you might want to reduce this to 1 over 3,960. Okay. Okay, here's another example. A letter is drawn from one box and placed in box 2. Then a letter is drawn from box 2 and placed in box 3. Finally, a letter is drawn from box 3. What's the probability that the letter drawn from box 3 is B? And you're going to call this event A. So here, in box 1 you have A, and B. Box 2 you just have A and B. Then box 3 you have A, B, B, B. Okay. And here's the tree diagram for that. So here on the first draw, it's either going to be A or B. Now notice you have 2 A's in the first box and 1 B in the in that first box as well. So the probability of drawing an A would be 2/3, and the probability of drawing a B would be 1/3. And then on the second draw, this time, now notice in this case here, if an A is drawn out of the first box and placed in the second box, this time you got 2 A's and 1 B. So that probability of an A would be 2/3, and the probability of B this time would be 1/3. Or if you draw a B out of the first box and put it in the second box, so now you have an A with 2 B's. The probability of A this time would be 1/3, and the probability of B would be 2/3. And then on the third draw, will be this. If an A is drawn out of the second box and placed in the third box, so now you have 2 A's, 3 B's. The probability of drawing an A on the third draw would be 2/5. A B, its probability would be 3/5. Well, if a B is taken out of the second box and put in the third, now you have 4 B's and 1 A. The probability of drawing a B will be 4/5, while the probability of drawing an A will be 1/5. And if a B and an A is drawn, if an A is drawn here, again, that's going to be 2/5, then 3/5 here. And then here for this one, this is 1/5 and 4/5. Okay, now the outcomes look like this, and then you have to multiply each one of those probabilities along the branches here. So in this case here, if we want to find out the probability of that the letter drawn from box B is a B, then that means we have to add this one, which is 12/45, this one, which is 8/45, this one, which is 3/45, and this last one, which is 8/45. So we add that together, you'll get 31/45. Okay. Okay, let's look at this situation of modeling games. There are 2 colored marbles and 1 white marble in a box. Gwen mixes the marbles, and Arthur draws the 2 marbles at random without replacement. If the 2 marbles match, Arthur wins. Otherwise, Gwen wins. Does each player have an equal chance of winning? Okay. Now, here we can model this using a tree diagram. As you can see here, for a colored marble, that's 2/3, and the white marble is 1/3. On the second draw, without replacement, there's only going to be 1 colored marble left, so that's 1/2, and a white marble, that's also 1/2. If a white marble is drawn, then there's no more white marbles to be drawn, so that will be a 0 for the probability, but there will be only 2 colored marbles left, so that's a 1. And those outcomes are listed and with their respective probabilities here. And as you can see here, the probability that the marbles are the same color is 1/3. Okay? While the probability that they are not the same color is only 2/3. That's these 2 outcomes here. That's 1/3 plus 1/3, that's 2/3. So the players do not have the same chance of winning. Okay? Right. And that would conclude this particular video on multi-stage experiments with tree diagrams and geometric probabilities.